Hi everyone, welcome back to what is the last installment, in fact, of Math 256. So this will be the final thing that we'll be learning in this extraordinary term. So let's get started. As usual, I'm Scott, and today the last section that we'll be covering is also the last section in the textbook. This is section 7.6, which has to do with what are called delta functions and impulses. So first off, let's discuss the Dirac delta function. So this is called the Dirac, as in Paul Dirac, one of the founding fathers of quantum mechanics. So this is the Dirac delta function. And notice I put function in quotes here, and the reason is because this is not actually a function in the usual sense. It is what's called a generalized function. So this is what is called a generalized function. And what it's used for is it's used as a substitute for the derivative of the unit step function, used as the quote derivative of the unit step function. UA of t. So, in particular, as far as we're concerned, we don't need to get into the metaphysics of the Dirac delta function too much. However, we will just make a note when we need to differentiate, quote, I'm going to put quotes on it, just put lots of quotes here in lieu of any getting ourselves bogged down in too many swampy metaphysical matters. So if we need to differentiate the undifferentiable function u sub a of t, we will write it as delta sub a of t. And in particular, what this actually represents is not a function in the traditional sense, but more like an operator. But that's not really actually so important for us right now. Let's just get into the details of how to do the Laplace transform of it. So, Laplace transform. Of the Dirac delta. Well, if the Dirac delta is acting like the derivative of u sub a, then let's just explore that road. So Laplace transform of the derivative of u sub a of t is going to be, according to the usual thing we know about derivatives and Laplace transforms, it's going to be an extra factor of s times the Laplace transform of just the u sub a of t, but then minus the initial condition, which is u sub a of 0. Now, as long as here we are assuming basically that this is equal to 0, then what we'll do is just write S times the Laplace transform u sub a of t. But what is the Laplace transform of u sub a of t? It's equal to, so this is S times e to the minus at, sorry, as, divided by s, and those will cancel each other. And so we'll just get e to the minus as. So there's that. Now, the use of this, the reason why we actually even need to explore this, is that there are certain physical contexts that we will get into when we start exploring circuits and such that require, or at least are facilitated by the use of a derivative of a function that, technically speaking, isn't actually differentiable. But in general, so this is used in situations where a sudden impulse is applied, and it's considered to be sudden enough that it's effectively discontinuous, but we still want to be able to do calculus with it. And calculus doesn't work so well if a thing is not actually differentiable. So examples would be something like collisions, and then maybe switches, and that's in electrical circuits. And those will be the main ones. Okay, so let's actually see what this would look like in something a little bit more concrete. So a disclaimer here, I am not an expert in circuits, and so what you're going to hear from me is basically just what a person who knows a few things about differential equations picks up by the wayside about circuits. So if you are at all involved in electrical engineering, then you probably know more about circuits as circuits than I do. However, we're going to be looking at them in this class from in the following way, and it's an interesting perspective here. So mechanical systems, and circuits, and electrical circuits. All right. So first off, if we go back and think about the springs as an inspiration. So springs, they can come with some extra features, such as, so first off, there's obviously the springy part. So this is a spring, and we have some mass, and then we can have a dashpot. And the dashpot is really just sort of a stand-in for anything, like say friction, that actually takes some of the energy out, absorbs some of the force in the system. So we've got here so this is a spring with constant K, so that's the spring constant from Hooke's law. Here's a mass, M, and then here what we have is a dash pot with a coefficient of C, and this represents basically friction. So you think of this as friction. Something where some of the energy is being lost in this whole process. And then the variable here will represent x, which will be the displacement from the equilibrium position. Okay, and then if we have an external force, of f of t, then the equation for this whole situation will be this. So m x double prime plus c x prime plus k x is equal to f of t. So it's capitalized not because it's a Laplace transform or an antiderivative or anything, just standard notation. Now, that's the situation for a spring. Springs are a physical situation that I have an easy time visualizing. They bounce back and forth, they oscillate, and if there's friction, that's going to be dragging on it. The mass is going to introduce inertia that has its own effect on things, makes it harder to get moving, but also harder to stop. I think I have a feel for how these things generally work. And then the spring constant is basically how stiff the spring is. So a bigger value of K means a stiffer spring, and a lower value of K means a looser spring. But now we'll go into another situation that I feel like I know a lot worse, or I know a lot less about. And that's an RLC electrical circuit. Now, the great thing about a math class is I don't know a lot about these, but I don't actually need to, because math is basically a big complicated system of analogies, and here you're about to get a doozy of an analogy. So here's what's going on in this. So we are going to have some of the following ingredients. So there's going to be right here, which we'll label with E for electromotive, but this is the source. It's going to be a source. The source of some of what is called the electromotive force. And then what we're going to have also in play here is a resistor with resistance R. There's a resistor with resistance R, and that's R ohms, but not that it really matters. I mean, it matters, but not to us. And then there's going to be over here an inductor. And this is an inductor with inductance L. And the reason why it's an L rather than an I for inductance is because the letter I is already taken for current. And then up here we're going to have a capacitor with capacitance C. Oops, capacitor. With capacitance C. And then right here what we're going to have is a switch. And so the switch up here can be turned on or off. Or really I should say, it can be opened like it is right now, or it can be closed. So you can close the circuit, or you can interrupt the circuit by opening it. Now whenever it gets closed, then what happens is the electromotive force here supplies voltage, and then that in turn would then register on the capacitor. But the important thing is not actually necessarily the meanings of all these, but the equations that we get. And the equations we get are coming from Kirchhoff's second law. So we don't need to know the details of this, so we won't. But as far as we're concerned, from Kirchhoff's second law, it would imply, so it implies the following. So basically, it implies that Q double prime of T, L times Q double prime of T plus R times Q prime of T plus 1 over C times just Q of T is equal to the electromotive force. So where Q of T is the charge, and so this would be the charge, and it would be in amperes. Sorry, charge is not in amperes, charge is in coulombs. In coulombs. Current is in amperes. Charge is coulombs. And E of T is the electromotive force or the impressed voltage. Okay, so the units of E of T are volts, by the way. But again, I don't want to get bogged down too much in this because it's a class all on its own. So then this can be rewritten if we know a certain thing, but Q prime of T, that is the same thing actually as the current. So the change of charge is the current, and that's what makes the current flow like a river, and that's why it's called current. So Q prime of T is equal to the current, which is I of T. And this is the current. And that's in amperes. Again, not that that's really so important, so we can rewrite this using that. So we can rewrite the equation. So the double derivative of the charge is the same as just the derivative of the current, so that would be L I prime of T plus R times I of T plus 1 over C times Q of T, and so what that means is still equal to E of T. which this then could be rewritten as the antiderivative of the current, which would then make it the integral. So Li prime of t plus Ri of t plus 1 over c times the integral from 0 to t of I of tau, and that's an integral with respect to tau, and that is all equal to e of t. This is what's called the integro-differential equation because it has an integral and a derivative. This is the integro-differential equation. But then, if we don't like that integral, we can rewrite this with a derivative. So if we differentiate, to eliminate the integral, and then what we would get is L I double prime of t plus R capital R I prime of t plus 1 over c times just I of t, and then that's equal to the derivative of the electromotive force, so E prime of t. But now this, as well as the original equation that we started with up here, well, way up at the top, those have the exact same format as the spring equation. So notice that the circuit equations have the same form as the spring equations. Or equation. So in the case of the spring, we had m x double prime plus c x prime plus k x is equal to the external force, the whatever is forcing the oscillations. In the case of the first version of the circuit equation, the one that involves charge, what we had was L times Q double prime plus R times Q prime plus 1 over C times Q, and that's equal to E of t. And then in the case of current, we had the same thing but with I. So we had L I double prime plus R times I prime plus 1 over C times I, and that's equal to E prime of t. So what this means is we have actually a network of analogies here. So this gives us what is called the electrical mechanical analogy, also known as the impedance analogy. So also known as the impedance analogy. So this is covered, by the way, in page 210 in your textbook, I believe. If you want to read more. So page 210 in the textbook. And basically we can sketch out here the network of analogous quantities. So first off, in the case of the spring, second off in the case of the charge, and third in the case of the current. Because we've got really two different versions of the circuit equation where in fact even parts of the charge and current are analogous with each other. So in the spring situation, the main variable we're talking about is x of t, which is the position, versus in the case of the charge, where what we're talking about is q of t, which is the charge in coulombs. So the charge is in basically the preponderance of electrons over protons or vice versa. And then current, which is the derivative of charge, is basically the flow of the difference in the electrons or protons. But the important thing is that's the variable that is being tracked in each of these cases. And then the other thing that is important to connect them as far as the non-parameters. So we have F of t, the external force. That corresponds with the electromotive force. Sorry, that's E of t in this case. It's the E of t, the electromotive force. And then here, in the case of the current, that's E prime of t, which is the derivative. Of the electromotive force. So it's not something that we're going to give even a name to, really. So okay, so we have the external force in the case of the spring, so that would be like if I were jiggling it. That is what corresponds with the source here, which is imposing its electromotive force or impressed voltage on the circuit. And then on the current side of things, it's the derivative of that that is in play. And then here, what else do we have? We have the mass, which for the purposes of the spring, the role played by the mass is the inertia that it has. And the inertia in the case of the spring corresponds with the inductance. And that's in both of these cases. So the inductance of the circuit, it corresponds with the inertia in the spring. Here we have next C, the dash pot, and we should just think of that as being friction. It's the place where the energy gets kind of absorbed or lost. And here, what is playing the role of the C is the R, which is the resistance, or the resistor. And that's the same here. And then lastly, here we have the K, which is the spring constant, in other words, like the stiffness of the spring. So a bigger value of K will cause a more intensive spring back. So this is the spring constant. And you can think of it as being the stiffness. Now this corresponds in the equations over here with 1 over C, which is called the reciprocal capacitance. And same here. Now this one I think is interesting too because it tells you essentially, so the spring constant is the stiffness. Higher values of K mean a stiffer spring, like you're talking about like maybe like an industrial spring rather than a slinky or something. So higher values of K would correspond with lower values of C. So more stiffness means like less play in the joints, and the capacitor is more or less giving you the play. Lower values of K means it's a looser spring, more like a slinky. That corresponds with higher capacitance. But anyway, so it's all well and good. But the interesting thing about this is we have here a derivative of the electromotive force. But if what we're talking about is something that involves a discrete change, like a sudden change, like the flipping of a switch, for example, then what that means is that we are going to be ending up with a situation where we have to take the derivative of a function that technically isn't differentiable. And that's why we're going to end up needing the delta function here. Now let's try some examples. We're just going to go with a whole treasure trove of examples here involving springs and circuits alike, which, as we now know, are basically two sides of the same coin. So let's think about how this will work if we have, for example, a spring such as the following. So we have a spring where the mass is equal to 1 unit, C equals 0, so it has no friction, K equals 4. So that's the spring coefficient, the spring constant. If this had been bigger, it'd be a stiffer spring. If it's less, it's a less stiff spring. And then let's say that the forcing here, the external force, is going to be equal to the sine of 3t. So we've got here is an external force that is pushing the spring back and forth. So it's applying pressure in a sinusoidal fashion. So it's pushing it out, pushing it in, also then pulling it back in. Okay. So then what we have here is x double prime plus 0, x prime plus 4x is equal to sine 3t. And what we can just do, and we need some initial conditions, and we'll start with some standard initial conditions. X prime of 0 is the same as x of 0. X of 0 equals x prime of 0, which equals just 0. Okay, so then if I apply the Laplace transform to both sides, then that's going to give me s squared x, capital X, minus some initial condition stuff, but since they're all 0, it's not going to apply, minus 4 times capital X is equal to, and then sine is the trig function, which means it's got a plus, t for trig, and then it's s squared plus k squared, so it's going to be k, so k is 3, so it's going to be plus 9, and then sine has the k, because it's like the opposite of what you'd expect. Cosine you'd think should have the k, sine should have the s, and it's reversed. Okay, anyway, that's just my own personal mnemonic for this. But anyway, now proceeding, we've got s squared plus 4 times x is equal to 3 over s squared plus 9 divide both sides by the s squared plus 4, and we'll have x is equal to 3 divided by s squared plus 4, s squared plus 9. And now if I want to do the inverse Laplace, I need to apply the method of partial fractions to expand this out. So then I will look at 3 equals mystery as plus b over s squared plus 4 plus mystery cs plus d over s squared plus 9. And so that means that 3 is going to equal as plus b times s squared plus 9 plus cs plus d times s squared plus 4. Now thinking about the exponents here, if I look at an s cubed, so s cubed, that's going to be coming from the as times the s squared and the cs times the s squared. But there's no s cubed on the other side. As for the s squared, that's going to be coming from the b squared, no a though. It's going to be coming from the d, so the b times s squared and the d times s squared. B plus d also equals 0. As for the s, that's only going to be coming from the 9a and the 4c. And that also equals 0. And then the constant. So that's going to be 9b and 4d. And that equals 3. Alright, well here what we have are different coefficients on the a and the c that are not a multiple of each other, and they end up equaling 0, and the only way that can happen is if a and c both equal 0. But I'll leave, but if you wanted to make that more official, you do a equals negative c, which in turn would mean negative 9c plus 4c equals 0, which means negative 5c equals 0, which means c equals 0, which means a equals 0. But in general, if you know this fact, you can use it. If you have different coefficients that are not a scalar multiple of the other ones that add up to 0 both times, then they must be then the two variables must be equal to 0. That's a fact. You can actually prove it using linear algebra. But anyway, so there's that, and then b equals negative d, which means that we've got negative 9d plus 4d is equal to 3, which means negative 5d equals 3, which means d equals negative 3/5, which then in turn means that b equals positive 3/5. Now if we look back at what we were calling each of these things, the b is the constant term of the first, so that means that capital X is equal to 3/5 times 1 over s squared plus 4, and then negative 3/5 times 1 over s squared plus 9. Now here, if we wanted this to be more inverse Laplaceable, we would want maybe to rewrite it with a 2 up there and a 3 up there, so that would be multiplying it by 2 over 2, for example. So So multiply the top by 2 can only be done if I also multiply the bottom by 2. And it's getting to the end of the term, so we better watch our step, write everything out. Never know. So with this one, I want to put a 3 up there, so I'll just transfer the 3 from that one. And here, what we've got is exactly what it takes in order to get the inverse Laplace, and we see signs. So this is 3/10 sine 2t minus 1/5 sine 3t. Alright, now let's do another example with a spring. And here the partial fractions is going to get a little hairy. But here goes. Okay, so it's going to be spring again. And the important things about the spring are going to be that the mass is going to be 1. The C is going to be 6, so there is now something pushing back, something absorbing some of the force here. And then we're going to have K equals 34. So in comparison with the last spring, although they have the same mass, this one is a lot stiffer. And then we're going to have an external force, F of t, which is equal to 30 sine 2t. Alright, now setting up the equation is a piece of cake. X double prime plus 6x prime plus 34x equals 30 sine 2t. Oh, and our initial conditions here, which will be the standard initial conditions, will be x of 0 is going to be the same as x prime of 0, which is going to be 0. So very common initial conditions that we'll see. Okay, so then we pass to the Laplace transform, which is going to be, in this case, s squared times x, and then there would be other terms if the initial conditions were not 0, but they are, so there aren't. S squared x plus 6sx, these are capital X's now, plus 34 capital X is equal to 30, and then we're talking about the signs, so that means k on top and s squared plus k squared on the bottom. Alright, so now what we've got here is s squared plus 6s plus 34 is times x is equal to, let's just combine them, 60 over s squared plus 4. So now we'll move that over there. So we'll have x is equal to 60 divided by s squared plus 6s plus 34 times s squared plus 4. Now neither of these can be factored, so when we have two irreducible quadratics like this, then that means we are going to be wanting to rewrite them in partial fractions, and we're going to have linear terms on the top. So 60 times s squared plus 6s plus 34 times s squared plus 4. It's going to be the same as some mysterious combination of as plus b over s squared plus 4 and cs plus d over s squared plus 6s plus 34. So then, that means that the 60 itself has to be the result of multiplying everything through by the common denominator, so that's going to be as plus b times s squared plus 6s plus 34 plus cs plus d times s squared plus plus 4. All right, now if we look at how things are going to shake out here, we're going to have on the s cubed term, so we can just see where these are going to come from. There's going to be an a s cubed plus c s cubed, no other s cubes will be here, and those equal 0, which means that a and c are going to be opposites, we know that much. As for the s squared terms, we're going to have, it looks like 6a plus, there's going to be a bs squared, and then over here we're going to have 4d, but no s squared on that term on that side, so it's going to be equal 0. As for the s terms, we're going to have, it looks like 34a. From this one, we're going to have 6b. And from this one, we're going to have 4c equals 0. And then from the constant term, we're going to have, looks like 34b plus 4d is going to equal 60. Alright, now let's see what we can do here. So we've got A, B, C, and D, and we've got 4 equations, and frankly, usually we do this by some kind of fancy algebra and such, but you've all taken linear algebra, so you know how we could set this up in a matrix equation. So A, B, C, and D. We're going to have in the first case 1A, 0B, 1C, 0D. In the second one, we're going to have 6A, 1B, 0C, 4D. Then we're going to have 34A, 6B, 4C, 0D. And then in the last one, what we're going to have is going to be 0, 34, 4, 0 and 4. And then those are going to equal 0, 0, 0, and 60. So if I wanted to actually do this using linear algebra, I'd just do 1, 6, 34, 0, 0, 1, 6, 34, 1, 0, 4, 0, 0, 4, 0, 4, augmented, 0, 0, 0, 60. And then I could rely on some form of technology to take the hard work off my shoulders on this. And in the process of taking a quick break to calculate that, I discovered a typo here, so that 4d should actually just be 1d. The s squared term here comes from d times that, not d times 4. So that means that this line of the matrix also will be a 1, as will this one. Okay, so then according to according to a TI-89 calculator, if I will reduce this corrected version, then what I'll get will look like this, which means that we are going to have an A of negative 10/29. We're going to have a B of 50/29. We're going to have a C of 10/29. We're going to have a d of 10/29. And so that means that our overall expression here can then be rewritten. So then we can write x equals negative 10/29. Now a represents the coefficient of the s over the s squared plus 4. And then plus 50 over 29. And then b is just the constant over s squared plus 4. Plus, and then the c and the d together are on top of this expression. However, looking at that, I can see that I'm going to have to complete the square on the bottom in order to reverse Laplace this, and so it'd be more convenient if I don't actually separate those out like I did the previous ones. But what I can do is I can pull out a common factor of 10/29 times, and then that's just going to be s plus 1 over s squared plus 6s plus 34. Now, those were the common factor that they shared there, which was convenient for me. Now I can complete the square. And if I want to complete the square of an expression like this, then I'll have s squared plus 6s plus 34 is the same as s squared plus 6s plus 9. That's the square that starts with a 1 and then has an x coefficient of a 6. But then that doesn't quite balance out, so I have to do plus 25. Okay, so then that's s plus 3 squared plus 25. Okay. Now here it'd be more convenient if that one were expressed as a 2 rather than a 1, because I need, if it's a constant, I need it to match the k there. So what I've got is negative 10/29 s over s squared plus 4. And the next one here, I'll borrow 2 from there, and that'll leave a 29 times 2 over s squared plus 4. Plus, now I want this expression to now involve just an s plus 3, not an s at all. So 10 over 29 times s plus 3 minus 2 over s plus 3 squared plus 25. So then when I expand it all out, or not all out, but somewhat out, I have 10 over 29 over s times s over s squared plus 4 plus 25/29 2 over s squared plus 4. And then over here, what I'll have is plus 10/29 s plus 3 over s plus 3 squared plus 25 minus, and now it's going to be 20 over 29 times 1 over s plus 3 squared plus 25. Now the only thing left that I would want is I would rather this had a coefficient of 5 rather than a coefficient of 1 on top, and I don't want to rewrite the whole expression just to make that happen, so it's the same as negative 4 over 29 and then 5. over s cubed, sorry, s plus 3 squared plus 25. Okay, so that's how that one would all end up. And then that means I can finally do the inverse Laplace, and what we have over here is a classic cosine. So it's minus 10 29ths. Cosine 2t. Over here we have plus 25 29ths. And it's going to be a sine 2t. Here what we've got is plus, and now this is a shifted, or a translated, in this case cosine, so it's going to be 10 29ths, and the way you do the shift is it's times e to the shift. This was shifted to the left 3, so minus 3t cosine 5t minus 4 29ths e to the minus 3t sine 5t. And that's that. Alright, now let's discuss how things are the same and how things are different when it comes to circuits. So practically what we're going to be using is the third version of the circuit equation. So we'll generally use the version that goes L I double prime plus R I prime plus 1 over C times I is equal to E prime of t. Now, unfortunately, so this is the most convenient one for most calculations. However, what's inconvenient about it is that certain pieces are not usually provided to us, and we have to do a little bit of work for them. So we won't typically have the I prime of 0 given to us, so we'll usually have to earn it. We have to solve. We have to solve for it in the equation. And the equation that we'll have is L, and it'll be the version, it'll be the second version of the circuit equation. L I prime of 0 plus R times I of 0 plus 1 over C times Q of 0 is equal to E of 0, where I of 0, this is the initial current, Q of 0 is going to be the initial charge, and E of 0 is the initial voltage. Okay. So other notes, the E of t will often be a piecewise function. Piecewise function. And it will involve parts where the switch is either open or closed. Piecewise function where open switches produce an impressed voltage of 0. And closed switches produce a non-zero. Impressed voltage. Alright, so let's just go ahead and try an example here, and the example is going to give us some of the details to begin with, and we're going to have to work out the rest. So the resistance is going to be equal to 110 ohms. The inductance is going to be equal to 1 Henry. The capacitance is going to be equal to 0.001 farads, and then we are going to be given that the circuit is initially passive, with initial voltage supplied by a 90-volt battery. So what that means is E of 0 is going to be 90 volts. Okay, and the initially passive implies Q of 0 is 0, no charge, no current. I of 0 also equals 0. Okay, well, that means we need to figure out I prime of 0. So if I put these pieces in here, I'm going to have 1 times I prime of 0. Oops, plus 0 times R. Oops. 110 times 0. Yeah, let's just start that all over again. So we're just finding the initial condition here. So 1 times I prime of 0 plus the R that we're given, which is 110, times the 0 for the initial current, plus 1 over 0.001 times the initial charge, which is also 0, is equal to 90, the initial voltage. So then that means I prime of 0 is going to equal 90. Okay. Now, we need a little bit more description for our electromotive force in this particular case, and let's say that E of t is the following. So E of t is the following. At t equals 0, the switch is closed. And the voltage is 90 volts. There is an electromotive force of 90 volts. At t equals 1, the switch is opened. And the electromotive force becomes nothing. So in other words, E of t is equal to the piecewise function that is 90 from 0 less than or equal to t less than or equal to 1, and then 0 for t greater than 1. In other words, e of t is equal to, and so this is a kind of situation that is best described using the unit step function. It's going to be 1 minus u1 of t. So this represents being equal to 1 until t gets to 1, in which case it will equal 0. Alright, well in that case then we are finally able to start working on our differential equation. So in order to do that I'm going to need an e prime of t, which the derivative of the unit step function technically doesn't exist, but for the purposes of solving the differential equation, it can be considered to be the delta 1 function. So the Dirac delta, named in honor again of Paul Dirac, one of the great physicists of the 20th century. Anyway, so that's e prime of t. Okay, so then that makes our overall equation. So the L, the inductance was 1, so that means we're going to have I double prime plus the resistance, which was 110 ohms, I prime, plus 1 over the capacitance times I equal to negative 90 delta 1. Delta 1t. So in other words, I double prime plus 110 I prime plus 1000 I is equal to negative 90 delta 1 of t. But now I can take the Laplace transform of these, and this is going to be s squared times I. Now this time we don't have initial conditions of all 0. We had I of 0 equals 0, and I prime of 0, as we saw, equals 90. So that means we're going to have to deal with that. So it's going to be minus s times I of 0 minus I prime of 0. Plus 110 s I, and it's going to be minus I of 0, so that one's going to equal to 0, so that's fine, and then plus 1000 I, and it's going to equal the Laplace transform of the Dirac delta function at 1, so that's going to be equal to negative 90, and then the Dirac delta function of a little a there is e to the minus as, so it's going to be just e to the minus s in this case. Okay, so then what have we got here? So this is just going to be 0, this is just going to be 0, so let's get everything organized. This is going to equal 90, so it's going to be s squared. I'm just going to collect together the s's, plus 110 s. Sorry, I'm going to collect together the i's, plus 1000, all times I, all minus the 90. Is going to equal negative 90 e to the minus s. So I can just move that over to the other side, and I'll have s squared plus 110 s plus 1000 I is equal to 90 minus 90 e to the negative s. So then I will divide in order to solve. So that's going to be s squared plus 110s plus 1000. And then this one over here is going to be s squared plus 110s plus 1000. So I'm going to cancel that with that. And so then I'm going to have I is equal to 90, actually I'll write it this way, 1 minus e to the minus s times 90 divided by s squared plus 110s plus 1000. Now this is a situation where we're going to need to use some partial fractions. So 90 over s, so this is, so this factors to s plus 10, s plus 100. Okay, so we're going to have 90 over s plus 10 times s plus 100. It's going to equal a over s plus 10 plus b over s plus 100. So this is going to be the easiest partial fractions we've had in a while. A rare change of pace here. So a times s plus 100 plus b times s plus 10. And that's going to equal 90. So now I can actually do my old classic trick of just setting s equal to helpful values. So if s equals negative 100, that's going to give us negative 90 b equals 90, which means b equals negative 1. And if s equals negative 10, that's going to give me 90a equals 90, which means a equals 1. So if I put those together, that means that the Laplace transform of my current is going to be equal to 1 minus e to the minus s times, and the a is just 1, so it's going to be 1 over s plus 10, and then the b is negative, so it's going to be minus 1 over s plus 100. Now I'm going to separate this out into the part that has the e and the part that doesn't. So that's going to be 1 over s plus 10 minus 1 over s plus 100. Then that's going to be minus e to the minus s times 1 over s plus 10 minus 1 over s plus 100. And the reason I did that is because when we have this expression right here, that amounts to the same thing as the shifted function that you get when you do when you use the unit step function. So this part is going to equal just e to the negative 10t minus e to the negative 100t. And as for this part, it's going to be the same thing, but it's going to be shifted. So it's going to be u1 of t times e to the minus 10 times t, and then it's got the shift of 1, so t minus 1, minus e to the minus 100 times t minus 1. Oh, sorry, and this is now I of t. Not capital I anymore. So there we have the formula for the circuit. This represents what the current was prior to the circuit being turned on, and then the circuit being opened. So and then the circuit is opened, and then what happens is the electricity works its magic. Now, one interesting extra thing that's that's very intriguing to know. Is that the impedance analogy, the electrical mechanical analogy that we just explored, that comes from the fact that the differential equations have the same form between springs on the one hand and electrical circuits on the other, actually formed the basis for the use of certain kinds of analog simulators of what would eventually become nuclear reactors. Before the first nuclear reactors and power plants and submarines and things like that were built, they actually did a simulated version of the mechanical system with all the forces and everything in play. But they did it not using an electronic computer like we do, but by using an electric circuit to simulate the masses. So they would set it up with inductors and capacitors and resistors, all of the right calibration, in order to run a simulation of what would be going on inside the nuclear reactor. So this was a very interesting application of this correspondence. But my personal favorite part about the analogy is that it actually gives me something to organize my mind around when it comes to the actual meaning of some of these electrical concepts. So I don't pretend to be any great expert on electrical affairs, and so for me to be able to try to get a feel for what inductance means, it's very helpful to me to know that it corresponds with basically the inertia of a spring. So it's basically so then I can just think of it as being the tendency to be hard to get started, or the tendency for the current or the charge to persist. Similarly, here the friction, the thing that takes the force out of the mechanical system. It's useful to me to have the idea that the resistance corresponds with that. So then I have a better idea what's going on with that. And then capacitance, I've never been able to really keep straight for more than a day at a time what capacitance means. But one thing that I can actually it can help me understand is the capacitance here is the reciprocal of the spring constant, and the spring constant is how stiff the spring is. So so the capacitance basically is how unstiff it is, how loose it is, how much wiggle room there is, and so that I find is a useful mental aid in trying to organize my mind around what these things are actually doing. All right. Well, anyway, that concludes this edition, and all editions for that matter, of Math 256. Thank you for joining me during this crazy term. It's been a real challenge for all of us, I assume, but now we have finally brought this chapter to a close. So, until we meet again, perhaps in some future class, I'll see you later. Bye.